Hey there, we're going to start off chapter 5 by talking about the relationships with what's going on within the triangle. So this section we're going to talk about mid-segment theorem and coordinate proofs. So getting into our vocabulary, the first thing we need to make sure we know is what's a mid-segment. So the mid-segment of a triangle is the segment that connects the two midpoints of two sides of the triangle, and within one triangle we have three mid-segments. So what do those words look like? And just to remind you, if at any point you need to slow the video down or pause it to write something or rewind it, that is also available. So in my triangle, to find the mid-segment, I need to find the midpoint of two sides, knowing that the midpoint definition says it is in the middle of the segment and it creates two congruent parts on each side. So if I connect the two midpoints of two of the sides, then that segment I just created is called the mid-segment. So if I would happen to find the midpoint of this side and then connected, I would find my other segment and my third mid-segment. So that is what the mid-segment looks like and what we'll be working with today. The second vocabulary is called the coordinate proof. So this involves placing geometric figures such as squares, triangles, hexagons into a coordinate plane, remembering that the coordinate plane is the XY axis. So getting into our theorems of this section, our first one talks about the mid-segment theorem. And the mid-segment theorem says, the segment connecting the midpoints, knowing that D and E are the midpoints, of two sides of the triangle is parallel to the third side and is half as long as that side. So we know now that DE is our mid-segment. And some terminology you might see is called DE is opposite AC. So DE is opposite line segment AC. This theorem also gives us parallel lines, so now we know that DE is parallel to AC. So that's one thing we can get out of this theorem. Another thing we can get out of it is that DE, the mid-segment, is half of the side that it doesn't touch, or the third side of that triangle. So those are the three things that we can get out of this theorem. So let's go ahead and check out how we can use this in an equation or a problem. So we have a large triangular window with the segment shown, and in this window we know that DF is a mid-segment. So DF is a mid-segment. Some things we might know: it is opposite BC. So the mid-segment opposite BC is called DF. We also know now from Theorem 5.1, DF is parallel to BC. So DF is parallel to BC. We also know that DF, our mid-segment, is half as long as BC. So using that information, we want to find the length of DF, and we know the length of DF is half of BC, or the side that it won't ever touch. So BC equals 1/2 of 90, because BC is 90 inches. So we now know that DF is 45 inches. All right, moving on, we also have been told that EF is our mid-segment. So from that theorem, we know that EF is opposite side AB, so it will never touch this side of the triangle, AB. We know that EF is parallel to AB because of Theorem 5.1. And last, we know that EF, our mid-segment, is half of AB. But what if we need to solve for one of the side lengths of the triangle? Well, we know that the side now of a triangle can equal 2 times our mid-segment. So we are going to multiply our mid-segment's length times 2 to find this side of the triangle. So AB is 2 times FE. So FE is 45, so we're going to take 2 times 45 inches to give us 90 inches for AB. All right, using that information, we're going to come over here. And here is some other terminology you might see. The mid-segment DE can also be called the mid-segment opposite BC. So this terminology is very important for you to know so you can solve your equations correctly. So here's example 1A, and you can stop this video and write down the problem. So we want to find the length of the mid-segment. So the length of the mid-segment says we want to be smaller than the side of the triangle, and we want to be opposite EF. Well, we know that the mid-segment is created by connecting the two midpoints of the other sides. So we're going to go ahead and connect that, and we're going to call that JH. And we know now that JH is the mid-segment. We also know its opposite, EF. We know that JH equals half of EF. And the third thing we know is that JH is parallel to EF. So since we know that EF is 45, we can plug it into this equation. JH equals 1/2 of 45. So we know that JH equals 22.5. All right, go ahead and stop this video and do checkpoint number 1, and then we will move on. All right, moving on to example number 2. Again, using that mid-segment theorem. In the diagram at the right, we know that QS is equal to SP. And with that information, we know that S is the midpoint. By the definition, we know that the midpoint is halfway between on that segment. We also know that PT is equal to TR. So from this information, we know that T is the midpoint. So if we connect the two midpoints, we now know that ST is the mid-segment from what we learned. And we know the mid-segment is opposite QR, it's parallel to QR, and it's also half of QR. So now we know that ST is parallel to QR by the mid-segment theorem. Or 5.1. All right, just a little quick review. If I have, I'm looking at PQ or QP, what is the mid-segment opposite of PQ? Well, if I connect the two midpoints, I know that VT is now the mid-segment. And if QP is 50, half of that would be VT, so that would be 25. All right, go ahead and stop the video and do checkpoint number 3, or number 2. All right, here is checkpoint number 2's answers. And we will move into example number 3. So we are going to place figures in a coordinate plane. So the directions are: place each figure in a coordinate plane in a way that is convenient for finding the side lengths. So when you see that, you should think from now on placing one corner at the origin, so we know that the origin is always 0, 0. So it is easy to find the lengths of the horizontal and vertical segments and distance from 0, 0. So place one vertex at the origin and one or more sides, if you can, on the axis, the x and y axis. So in a square, let S represent the side length. So notice we are placing it in the origin and two side lengths are on the x and y axis. So normally we're going to go over some amount of units to place that, to get our ordered pair there. This time we're going to go over S units, so we would place it as S, 0. Sometimes we can think of it as maybe 2, 0, but right now we're going to use S because it doesn't matter what type of square it is, it will always come out as S units. All right, we're going to go up S units. That way we can say this ordered pair is 0S, or normally we see it possibly as 0, 2. And since we go over S units and up S units, our fourth vertex is going to be S, S, or sometimes you would think of it as 2, 2. All right, and for an acute triangle, we will need 3 different variables because of 3 different amounts of lengths that we go. So again, placing it in the origin and one side on an x and y axis. So we're going to move B units to get B, 0, or normally we would possibly think of it as 4, 0, whatever amount of units you want to use. And then we need to use 2 different variables because we're going to go over A units and up H units to find this vertex. And we're going to use 2 different variables because we're moving different units. So maybe we could think of this as 2, 3. So that that coordinate proof is for many, many different types and sizes of shapes. So in example 3, we want to find the length or the distance of the diagonal and the midpoint. So just as a refresher, if you want to stop this video and write down your formulas, you can. We're going to find the distance of BD. So we're going to put x1, y1, x2, y2. And we're just going to plug it in. So don't really make it any different than normal. S minus 0 squared plus S minus 0 squared. You would then get S squared plus S squared, which gives you 2S squared. And knowing how to break that down, square root of 2 times square root of S squared. Well, I can't simplify square root of 2. But I can simplify the square root and the squared. We know that S now comes out in front to give us S square root of 2. So that would be the distance of the diagonal of any square. So we could plug in S, whatever our length is, to get our diagonal distance. Now for the midpoint, again, plugging in the same way, S plus 0, S plus 0. So for any diagonal of a square, our midpoint is going to be our side divided by 2, our side divided by 2. So go ahead and stop it here and do checkpoints 3 and 4. And replay it when you get done. Here are the 2 answers for 3 and for 4. And then here is your homework. Feel free if you have any questions when I see you next to ask if you don't understand something. But until then, have a great day.